Hello, today we're going to be doing standard 5.5, which is on the behavior of wave functions. We're going to be looking at problem 5.33 out of McIntyre. And the question states, for each of the potential wells shown in figure 5.32, which I have those drawn below, we're going to make a qualitative sketch of the two energy eigenstate wave functions whose energies are indicated. For each energy state, we're going to identify the classically allowed and forbidden regions, then discuss the important qualitative features of each state. So, to start, we of course need the qualitative sketches, so I'm going to zoom out a bit so we can view these properly. So we have this bit right here. We have in green will be the potential well, similarly for the second one. We also have the wave functions for each of the energy eigenstates. But before we discuss those, we're going to talk about a little bit after these pictures in order to kind of gauge why the wave function looks this way. Kind of look at the different things that make us be able to derive this wave function quantitatively without actually knowing exactly what the wave function is. So I'll talk about more of this later, but let's look at the second one. So for this one, we have similarly here, we have our wave function, or our potential well drawn in green. And this one's a little more symmetric rather than the increasing one here. However, we're going to get similar patterns and we'll be able to use the same analysis to talk about what's happening in each of these regions. So zoom back out, and now we can look at what we need to describe these. So to correctly describe these functions, we're going to need to look at a few important necessary features. So first, if the eigenstate is in the well, we know that the solution is going to be oscillatory because the solution to the differential equation according to this part of the wave function is going to be a sine curve. And we know that since it's a sine curve, it's going to have a wavelength associated with it, and we'll call this lambda sub e. And this is going to change based off of both the potential and the energy value itself. And this wavelength follows this proportionality, that the wavelength is proportional to 1 over the square root of e minus the potential v of x. And we know that the amplitude is going to change inside the well in an analogous way. And what this means is that as the energy value and the potential get closer together, we know that the wavelength is going to get larger and the amplitude is also going to get larger. Therefore, we're going to have a smaller frequency between our waves. So similarly, if the eigenstate is outside the well, we know that the solution is going to exponentially decay with some decay length. We're going to call this L sub e. This decay length follows a similar proportionality, but it's proportional to 1 over the square root of v of x minus e. And this is because in this region we know that the potential is greater than the actual energy value, which in classical mechanics would be a forbidden thing because we're not allowed to have a negative kinetic energy. And the reason this is because typically we define kinetic energy to be 1/2 mv squared, and since all those values are non-negative, we have a non-negative kinetic energy. So this would typically be forbidden because we'd get a complex value here. But inside the potential well, is classically allowed. However, like I said, if the energy is less than the potential, we get classically forbidden. And if this potential well is infinite, so the potential at one point is infinite, we're just going to get a boundary condition of 0, and then the wave can just bounce back and forth with no decay. It will go infinitely. However, if we look at something more realistic, like a finite potential, but still have that the energy of the particle or the eigenstate is less than the potential, we know that the wave function is actually going to be non-zero in this region, even though normally this would be classically forbidden. And this idea is known as barrier penetration. This leads to the phenomenon known as tunneling. And when it's in this area, the particle is going to exponentially decay, and we also get this from the differential equation and the boundary conditions set up from the finite square well that we have there. So now that we have some of this, we can actually start talking about what's going to happen and how we can look at the wave functions for each of these. So let me zoom out once again. Okay, so for the first one here, we notice at the left we have a infinite square well where the particle or wave function will start. And then we have a constant 0 potential. Then we have a linearly increasing potential, and then we have 2 jumps, but both finite. So here we have the 4th energy eigenstate and the 11th energy eigenstate. For the 4th energy eigenstate, here we have the oscillatory portion because we're in a classically allowed region. And then when we hit this little well here, and what's it called? The energy is no longer above the potential. It's now less than or equal to the potential. We start getting this decay or tunneling. This is where it will exponentially, in this case, it's going to increase, but it's going to hit the decay. It's going to hit the it's going to hit this wave function equal to 0. This little dashed line here. And another thing we can note is, since this is the fourth energy eigenstate, we're going to have 4 antinodes noted here, 1, 2, 3, and 4. And here are the amplitude and wave function, or the wavelength, are slightly estimated. However, this should be roughly accurate. And here we also have the 11th energy eigenstate. And since noting the proportionality constants below here, we know that since this distance between the energy and the potential is greater, we know that the wavelength is going to decrease here. We're going to have a higher frequency of waves. So here, the waves are going to go a little faster, and as we go up the increase, the wavelength's going to slightly increase as well. And then when we jump up here, we're going to get a constant jump. Because the potential is constant, the wavelength will also be constant. And then once we hit, we're going to have 11 antinodes, similarly to the 4 here. And we're going to hit here, and we're going to exponentially decay to the wave function being 0 here at this dashed line. This will go off to infinity. Alright, so similarly, we can do some analysis on this one. So we have the 5th and 10th energy eigenstates here instead of the 4th and the 11th, but we're going to get similar things. So here for the 5th one, the wave function is going to start in a classically forbidden region, which means that we're going to have this decaying function going off here to 0 or negative infinity, however you want to consider it. And then when we get into the well itself, we're allowed to be in here, and then we start oscillating. So we're going to oscillate back and forth with some constant wavelength because we have constant potential. And then once we hit, we're going to have 5 antinodes once again, and we're going to decay into this region here off to infinity. And then similarly, if we look at the 10th eigenstate, here, this shouldn't be so much bigger than this, but however, to kind of fit it into the way I drew it, it kind of is noted that way. But the important thing is we're going to have 10 antinodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also, we're going to have a constant wavelength here. And then since the distance between the energy and the potential is greater here, we're going to have a shorter wavelength, which means a higher frequency once again. And then this is still going to be constant because constant potential. And then we're going to jump back up to a higher wavelength. And then once we enter into this part, into this finite square well, where the energy is less than this potential value, we're going to exponentially decay to this asymptotically, and we're going to hit this wave function equal to 0 once again. So okay, that'll be it for the end of my video. Thank you. Bye.